Okay, welcome everyone. It's New England Dynamics Number Theory Seminar, and today our speaker is affiliated with Moscow, but he is in Uzbekistan, far, far away from New England, but the connection still works. So I'm happy to introduce Nikolay Moshchevitin, who will talk about inhomogeneous Diophantine approximation. Welcome, Koля. Are you muted? You're muted again, I think.
Sorry. Yes. So, Dimas, thank you very much. I'm very happy to speak in Brandeis. I am also, I always happy to visit Brandeis, even virtually. So today I will speak about something.
I'm in Princeton now, but it doesn't matter.
You are in Princeton.
We have a few people from Brandeis.
But the seminar is affiliated in Brandeis.
It is, yes. So we're
generally
we can think at Brandeis.
Okay. 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 So I want to today I want to recall some well-known facts and maybe not very well-known facts, simple and maybe not very simple, which I was thinking about for some years, some early results, and maybe some even new results. So, but nevertheless, I want to start with some. So, first of all, I would like to say, what do I mean by homogeneous and inhomogeneous approximations? And I will start just with this simple one-dimensional case. Some of the results which I will speak about will be related just to this simple one-dimensional case. So I can draw here at the screen some kind of geometric interpretation. Do you see my R2
yes, it's
plane?
It's a beautiful plane.
Yes, I see it works. I see it works. So to explain what is homogeneous approximation, I can draw, say, line through the origin. It is y equal theta x, and I am interested in finding integer points close to this line. So everything is quite simple. So, well, and if we deal with inhomogeneous approximation, we have another line which is parallel to that line, which can be written by such a formula, and we are interested in integer points close to this line. So this is the simplest one-dimensional setting. However, if we turn 2, which is equal 1 plus 1, here is R1, and here is R1, into D, which is equal M plus N, we may consider, instead of one-dimensional line, here m-dimensional linear subspace. Here, instead of R1, will be Rm, and instead of this R1 will be Rn, and we are interested in integer points close to m-dimensional linear subspace. This is a homogeneous setting, and m-dimensional affine subspace. This is inhomogeneous setting. And for homogeneous setting, as well as for let it be homogeneous setting, an important object is irrationality measure function. This is psi. Here theta may be number or maybe matrix. In this case, when d equal mn, theta is m times n real matrix. So irrationality measure function is the function which takes care on the best approximations. Let it be here x theta, or let it be here theta x. Here I write x less than t. So if m equal n equal 1, then it is just an integer number, but in general it is an integer vector, and this distance to the nearest integer is also multidimensional. This function determines almost everything. Best any question? Best approximations and so on. Well, this is the objects which I will speak about, and homogeneous problems are important to study in homogeneous problems. Now I am turning my talk to simplest inhomogeneous setting, and it is approximation theorem. Oh, one moment, did I change the slide? Oh, I see. So can you see my second slide?
Now it's slide number 3, I think. Is it okay?
Is everything?
Oh, the first one was the title.
Yes, okay, 3, yes, with Kronecker's theorem. So I will introduce. Yes, first was the title, so everything is okay. So I will formulate well-known Kronecker's theorem, and I introduce notation which are convenient for me. So theta is just that matrix which was handwritten on the previous slide. It is reasonable to consider an extended matrix as I said. We are interested in finding integer points close to inhomogeneous, to affine linear subspace, to study approximations to this subspace. We need irrationality measure function, homogeneous irrationality measure function for in dual setting, for the transposite matrix. So theta t is transposite matrix. And a convenient formulation of Kronecker's theorem is as follows. Let the following situation happens. In terms of irrationality measure function for the dual setting, it means that the function does not vanish. Then we have the following well-known density result. So if we deal with integer points of such a form, then theta z form a dense set. So for any epsilon, we can approximate this in homogeneity by a point of lattice as close as possible. So without a quantitative form, and the fact that we do not have a quantitative form here, in some sense, is strange. So I am going to my next slide, and now I will try to explain what do I mean that the fact that we have here just epsilon, but not a quantitative value in terms of something like irrationality measure function. I will try to explain, but one moment. So now I am coming back to one-dimensional setting. And what do we see here with respect to quantitative version of density result? First of all, for homogeneous setting, we have wonderful Hurwitz theorem, which can be extended to inhomogeneous setting. So here I recall Khintchine's theorem, which gives a quite similar bound as Hurwitz theorem for inhomogeneous result for arbitrary eta here. There is a lot of interesting problems related even to one-dimensional case. I do not want to go in details now, but nevertheless, I want to mention that although Khintchine's theorem has exact constant here, it is not the last word in one-dimensional problems. If you restrict yourself by other etas, then we have something maybe very interesting, but I do not have enough time to speak about this. Here I formulated one of the results which can generalize Khintchine. For instance, this unusual constant 27 over 28 square root of 7 arrives as an optimal constant for the setting when eta is not of the form m alpha. Oh, sorry, there is a mistake. No alpha, it is a mistake. It is from something here, theta. Of course, this is theta. Khintchine's theorem is optimal, for instance, when we consider eta equals 0, but if eta is not of such a form, there is a theory. Some of this theory, I think, is maybe not completely, but forgotten now. So, but why it happens so? I am going to my back slide. In general setting, we do not have quantitative bound. We have just epsilon here. Why? For dimension 1, we have 1 over q. I will try to explain it, and it seems to me that I have discovered some absolutely easy fact which was not documented before. So I will speak about it in few minutes. So, well, okay. Well, to start to understand well homogeneous problem, and to understand well homogeneous problem, we need to know Khintchine's Palermo's paper, which was the main paper which founded a modern Diophantine approximation. So the concept of uniform approximation, singularity phenomena, lacunary sequences, transference principle came from this paper. Now I am not in Moscow, but in Moscow, in my place, I have many relics, and one of them, this of print of Khintchine's paper in this wonderful journal, Rendiconti Circolo Palermo, with this wonderful medusa. Well, okay. So, and if we look at the first page, we see that it starts with well-known Kronecker approximation theorem, which we are speaking about, which I'm speaking about now. So let's continue. I wanted to show you this paper. Well, few words from Khintchine's Palermo's paper. I am interested just in two first moments here: uniform approximation and singularity phenomenon. What is uniform approximation? Uniform approximation, the first observation by Khintchine was that for one-dimensional case, we do not have singularity. If we look for irrationality measure function, here is the graph of irrationality measure function, then this graph should not lie under the, if here we have t, so 1 over 2t, it is not possible that the graph lies, then the slope lies completely under this 1 over 2t, it should go out. This is the first result by Khintchine, and the optimal constant here is Sekerish constant. But if we deal with higher dimensional case, just simply with linear form in two variables, then we have a singularity phenomena, which was discovered by Khintchine, and singularity phenomena says us that for any function decreasing to 0, we can find a degenerate vector. So I have forgotten to write here that theta 1, theta 2, and 1 are linearly independent over Q. Oh, no, I wrote it here. Look, this means that they are linearly independent. So the function is bounded from 0. So, well, so we have irrational numbers such that the slope of irrationality measure function lies behind a given function phi. And if we deal with simultaneous approximation, the situation is a little bit different. You should assume that the function is not decrease to 0 not very fast. So for linear form, you can take function which goes to 0 arbitrarily fast here, but for and it is clear, because if we restrict this value just by one component, we have one-dimensional case, and we do not have any improvement in one-dimensional case. So I recalled Khintchine's paper, and then I would like to recall a general result which appeared a little bit later. So well, a general result was documented by Yarnik. He considered general case of matrix theta m times n real matrix, and in the case, so m is the number of variables. Number of variables and n is the number of linear forms. So m is the dimension of subspace. Which we approximate to. So in the case when the dimension is greater than 2, it is not a one-dimensional subspace. We have a result similar to one linear form, similar to that one. Similar to that one. And when we have just one line, we have simultaneous approximation result. So what it gives to inhomogeneous setting. So you see here in red, I wrote two different assumptions related to the difference between case 1 here and case 2 here. So in case 1, we have arbitrary function decreasing to 0, and in case 2, related to simultaneous approximation, we need additional assumption. So what happens? So due to existence of singular matrices, we can say that we cannot improve this epsilon in general case. So that is why it is not possible to have any reasonable quantitative form of Kronecker's theorem in the case when we have two linear forms or more. But in the case when we have just one linear form, we have different initial assumption, something like this. And this explains why do we have such one-dimensional result with 1 over q. But if we look for higher dimensional analogs, higher dimensional linear forms in this setting, surprisingly, we find out that we can formulate something a little bit more stronger. If we have linear form in 2 or more variables, instead of one-dimensional 1 over q, we can write for any epsilon such a very weak improvement. This is almost obvious, and this cannot be improved to any quantitative result because of this case B in Jarnik's theorem. And the existence of this epsilon here can be explained by Jarnik observation from his famous Tbilisi's paper, where, among other results, he showed that if we consider two-dimensional lattices generated by two successive best approximations, then the determinant of this lattice tends to infinity lambda 2 nu. lambda to nu, when nu goes to infinity. I will speak a little bit later about some applications of this simple observation. However, I would like now to continue with Khintchine's paper, and I want to show some other problems related to this paper and some other connections to maybe rather modern or not so modern results. So another result which was discovered by Khintchine is an inhomogeneous theorem which states that for any theta we can transform linear form in one variable into badly approximable inhomogeneous linear form. This Khintchine's result had modern development. In particular, some time ago, Jimmy Tseng proved that the set of this inhomogeneities eta form a winning set, and there was an extended story about multi-dimensional generalization of history. However, I will come back in a few minutes. Well, okay. Nevertheless, I will speak again about multidimensional generalization. Well, this result by Khintchine was generalized by Khintchine himself and by Jarnik. The results by Khintchine were very well known for everybody, and Jarnik's papers were forgotten. But now I will not speak about Jarnik's paper, but I will speak about just Khintchine's result. So what is multidimensional version of this theorem? It is interesting because Khintchine himself stated it in such a way. So this is one of possible generalizations. But there is an interesting story related to this generalization. If we look for Khintchine's paper, we will see that he proved something like this. So, well, what is singular matrix? Singular matrix is just something. So here is a Dirichlet value for which, so for all matrices, if we consider the function Tm minus n, then the irrationality measure function will be below the slope of this T minus m over n. But if we put here additional epsilon and assume that for any given epsilon asymptotically the slope of the function lies below this epsilon T minus n, we get the definition of a singular matrix. I think that for dynamists much more convenient to use another words, the trajectories which go to infinity. But so I will speak in this. Khintchine proved a nice theorem which shows some relations between inhomogeneous approximations and singularity. He introduced so-called Chebyshev's property, which says that for any eta here, there exists a constant such we have infinitely many good approximations. Or maybe I should not write. Maybe I should not write here these brackets. I mean theta x here. So brackets here maybe not necessary. So for any eta, we have good approximations with respect to theta, which if theta satisfies this property, it calls Chebyshev's property. And Khintchine proved that Chebyshev's property is equivalent to non-singularity of matrix theta. Sometimes I am reading or rereading well-known books. And once upon a time, while reading Castle's book, Introduction to Diophantine Approximation, I realized that this Khintchine theorem is formulated in Castle's book in a different manner. In Castle's book, the constant gamma is universal. So the quantification has different order. I try to understand why does it mean. And surprisingly, I was not able to give a direct proof that Chebyshev's property is equivalent to Castle's property. I have a certain proof, but which of course is related to original proof, but it's rather strange that we cannot prove the equivalence of these properties directly, so that we cannot interchange the order here immediately. Okay, so this is another observation. So another story about inhomogeneous problems is as follows. Or I said you that few minutes ago so that I will skip some history. So no, it is not true. I will not skip some history. Oh, sorry. I will not skip some history. So here is some history which continues the Khintchine's theorem about existence of this badly approximable eta. Well, there is a lot of papers which deal with these inhomogeneous elements eta, which makes linear form badly approximable. And one of the results is as follows. If we deal with arbitrary metrics and look for this set of these etas which make the system of linear forms badly approximable in inhomogeneous set, we observe that this set is very large. Of course, it is a zero set, but nevertheless, it has full Hausdorff dimension, and it is winning in many senses. It is winning in Schmidt's sense, but now it is more popular hyperplane absolutely winning property. So it is hyperplane absolutely winning. I do not have time to explain what does it mean, but I want to say that the situation becomes a little bit more difficult if we deal with famous weighted setting. So I also do not have too much time to speak about what does I mean by weighted setting. But it is a standard and well known for our community setting when we deal with something like Schmidt's conjecture, when we for instance, have two numbers, and we approximate one number with approximating order something 2/3 and here 1/3. So these are weights. So these 2/3 and 1/3, they are weights. So 2/3, 1/3. So, and in general setting, we may consider a similar problem for systems of linear forms. We can put weights. We can put weights here for values of linear forms and here for values of coefficients. And in fact, it happens that in weighted case, it is not difficult to prove that this set for any matrix theta has full Hausdorff dimension. But as for winning property, it seems to me that the question is now still open, because the situation for winning property may be a little bit different. Under certain additional assumption, such as that matrix itself is badly approximable, it is possible to prove a very strong winning property. We call this absolutely, we call this not absolute, isotropically winning properties. What does it mean? So winning property means that we can win the game in the whole space. But isotropically winning property says that if we have a space, here it is RD, not D, what I don't know what R reservation. We may consider subspace here, and for any subspace we can win the game when we play just in this subspace. So winning happens isotropically. It doesn't matter what winning we're speaking about, Schmidt's game or hyperplane absolutely winning game. The definition may be adopted to both situations. However, this isotropically winning property is a very strong property because, for instance, for badly approximable matrices, trivially, we do not have isotropical, for badly approximable matrices, for badly approximable linear forms, we trivially do not have isotropically winning property. But nevertheless, we have isotropically winning properties for the set of these etas. And this is a specificity of the situation when theta belongs to badly approximable matrices. Because if theta does not belong to badly approximable matrices, there are examples that the set of etas does not admit isotropically winning property.
So what's the relation between isotropically winning and absolute winning? Not hyperplane, but
yes. This is
Macmillan, is it?
If it is not isotropically, it is a good question, but I want to give a comment on absolute winning. You mean Macmillan absolute winning property?
Yes.
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 This is in fact absolute winning property is something like one-dimensional property in general. So we know the sets which satisfy absolutely. We know only, roughly speaking, one-dimensional sets which satisfy absolutely winning property. And this example of not isotropically winning properties shows that the set constructed here is not absolutely winning. So if we have isotropically, if we have absolutely winning properties, then we have isotropically winning property.
Yes, but
so if it is not isotropic, but it is not surprising because isotropically absolutely winning property is roughly speaking a property of a one-dimensional set.
But do you know that this set with equal weights? Do you know that the set is not absolutely winning?
No. I don't know.
Okay.
And it doesn't follow from these examples which are it doesn't, in any case, it doesn't follow from these examples which I'm speaking about here, because these examples do not exist in the case with equal weights, because in equal weights we have isotropically winning property.
Okay, sure. So maybe maybe it's even absolutely winning.
In my opinion, it is not likely. So maybe I'm not able to answer right now. So I need to think a little bit more about this. So, but well. No. Maybe I don't remember well. I don't remember well. So I don't remember well. Maybe this example. Maybe this example can be adopted, and even maybe it was adopted to equal weights. I don't remember well.
Okay.
I should look inside the paper, because that time we were interested just in the difference. We wanted to answer a question why we are not able to prove winning property for weighted case without bad assumption for the matrix theta, and we did not think much about what this example means in general. Okay, I want to continue with another story about inhomogeneous approximations. Okay, so and as for another story, I will begin from another branch of number theory, from another direction. So let me recall you a simple exercise for students. Well, you see, n is the least common multiple of first numbers. Then we have a nice prime number formulation of variant of formulation of prime number theorem, and then we can see that among first numbers there is no numbers coprime to this least common multiple. So this is an easy exercise for undergraduate student, but if we think a little bit more about this, we will come to a very non-trivial concept on Jakob-Stahl function. So this is Jakob-Stahl function. The argument of my previous slide gives a log lower bound for Jakob-Stahl function, in fact, but Jakob-Stahl function itself is a serious object of is a important object, non-trivial object in analytic number theory, and so here is the definition, here is the conjecture by Jakob-Stahl, and here are best results, which are absolutely non-trivial and really difficult. So I am not so good in mathematics to understand all the proofs. Maybe I am able to read Ibanez upper bound, lower bound is a very recent solution of famous Erdős problem. If you are interested in more details, you can look into all the survey by Erdős. So without this Fn, it was an older result by Rankin from 30s. But as for one-dimensional case, so Jacob-Stahl function is something from one-dimensional case. So as for one-dimensional case, the situation is very difficult, and a lot of serious people are trying to improve upper and lower bounds here, and there is a gap. But if we deal with multidimensional analogs of similar problems, then the situation becomes easier, but not very easier. So if we stay in analytic number theory, we can found a simple and beautiful paper by Erdős, which was not improved up to now. What does Erdős paper deal with? So look, again, we consider R2. And in R2, we consider a square which consists of non-primitive points. What is the largest side of a square which consists of non-primitive points? Erdős proved two theorems in 50s in Canadian Mathematical Bulletin. This paper was forgotten for some time, but nevertheless, there is a story. I will say a few words about it. So, well, so the first theorem, it is just application of Chinese remainder theorem and prime number theorem, constructs a square with non-large square of such a size with non-primitive points. And the second theorem, which deals with rather simple sieving, says that if the square is large enough, then there is a primitive point in the square. As far as I know, no modern improvements of these Erdős results were obtained. Why I'm speaking about such special problems? So I promised that I will speak about homogeneous and inhomogeneous approximation. So my next slide will give some explanation. After this paper by Erdős, oh, sorry, before explanation, I would like to recall inhomogeneous result by Khintchine from my first slides. So if we deal with inhomogeneous approximation, we have this 1 over q bound even with constant. But why I'm speaking about Erdős? Well, next slide. Next year, after his first paper was published, Erdős and Csok applied these results on non-primitive and primitive points to obtain a result in Diophantine approximations with coprime setting. So you see, to have this coprimity in approximation, you should pay something. Instead of this 1 over Q, which comes from Khintchine and Chebyshev, you should have this additional factor, which comes from simple analytics. And what is an optimal bound here is an open question with an interesting history. So the history is here on the next slide. What I can say, the result of Erdős and Csok was forgotten, and in modern history, people started to reprove some results related to this topic. The upper bound was not improved. But as for the lower bound, it was proven by Zhytomyrskaya and Liu that it is not possible to have a constant here. But I think that if you look into Erdős proof and into something else, you will get such a result, which I decided to publish in the same journal, Canadian Mathematical Bulletin, in what Erdős Csok and Erdős paper were published. Well, however, the gap between upper bound and lower bound remains large enough. But what I can say, to get this result, you do not need just Erdős argument and Chinese remainder theorem. You need an inhomogeneous version of some result related to Legendre-Fatou theorem. Well, I will say a few words. So I recall your famous Legendre theorem about the structure of this 1 over 2 Q square approximations, that their convergence. Less known result is due to Fatou, which describes the approximation, all the approximations with 1 over Q square. They should be either convergence or intermediate fractions, and in general, if we have approximations of order 1 constant over Q square, then they are some combinations of convergence. It is a result by Worley, and to prove this, you need an inhomogeneous version of Worley's theorem. So I have just 5 minutes left, so I don't have time to speak about what does it mean. I want to say that this homogeneous setting was some years ago quite popular, and there are some metric results, so I just mentioned that they do exist. But I want to say that if we if we consider multidimensional setting with coprime approximation, when we approximate not one number but a subspace of high dimensions, then everything becomes trivial. So we have for simultaneous approximation, we have just analog of Kronecker's theorem with this epsilon, and this epsilon cannot be improved. And for one linear form, we have analog with this epsilon over Q, which I was speaking about a few minutes before. And to obtain this result, you need classical methods, successive minima, Mahler's theorem, and shifting of fundamental domains of lattices. But if we look into details of these classical methods, you will find something unusual. First of all, I want to speak about Kronecker's qualitative result with this epsilon. We can improve it a little bit. It is almost trivial that sorry. To have inhomogeneous result, I told you homogeneous result, you should have something corresponding homogeneous. And to have inhomogeneous Kronecker result, you need to have a result related to SL2 approximation to find SLD approximation to find fundamental domain close to linear subspace. So we have linear subspace, and we need to find a fundamental domain of an integer lattice close to this linear subspace. And what we can do, we can prove that in epsilon neighborhood of a linear subspace, you can find fundamental domain. You can find SLNZ approximation. But it is the only result we can prove. As was conjectured by Nikolay Moshchevitin, it is not possible to, just in the case, for instance, for simultaneous approximation, for approximation to one line. So it is not, it is possible to find such a vector for which there is no reasonable approximations by vectors which form a unimodular matrix. So for any order of approximation, you can construct such a vector which does not admit any SL3Z approximation. This proof is rather cumbersome, and I am afraid that up to now the methods of parametric geometry of numbers will not give an alternative approach. But what I had emphasized in my lecture now is that this very simple and easy result about epsilon here for one linear form has never been documented. So I would like to formulate a conjecture related to this hypothesis by Nikolay Moshchevitin, which was proved recently. So I said that this result is quite cumbersome, so I expect that the solution of the conjecture from my last slide will be also a little bit cumbersome. So what do we have? Now I recalled the epsilon result here, and it is easy to prove that this result holds for matrices also. But I want to conjecture that you cannot replace this here epsilon by any function decreasing to 0 slowly. I did not think about this conjecture for a long time, but in my opinion, it should be possible to construct such an example. So I would like to encourage some people to try to do this. Probably now it is time to stop. So thank you for your attention.
Okay, thank you, Nikolay. This was a very entertaining talk. Any questions to the speaker? So if there are no questions, could you still say a few words about this Worley's theorem and
It is
homogeneous? What does it mean? Worley's theorem.
Yes, it is.
You need some continued fractions. So if you have inhomogeneous approximation, you are using inhomogeneous continued fractions, or is it just continued fractions of theta?
I will.
It was earlier.
In fact, we use ordinary continued fractions, but
right. So here is
where is this Worley? Where is this? Yes, here. So
what's the statement?
Worley's theorem is just, it is not difficult observation. This look. If we have a rather good approximation to theta, then this approximation should come from convergent approximation. So it should be a linear combination of convergent approximations with these coefficients bounded in product. It is a very natural and very useful tool everywhere, because if you want to find certain approximation to theta with certain properties, for instance, if you want to approximate theta by of such a thing, this is a famous analytical problem. Sorry, I was out. I was out for some time. If you want to find an approximation theta by special sequence, and you know that it should be small, it should be a linear combination of convergence.
Okay.
So if you deal with inhomogeneous approximation, you do not have such a precise result, but you can use similar argument. If you, for instance, if you look for approximation for affine subspace, and if you have here many points, then you can shift these points by one of them to homogeneous approximation, and then observe something with Worley's theorem. This is what we do here.
So you are using, so you have theta and eta, and you're using continued fractions for theta.
This is not just exact what we do, but the structure. If we deal with inhomogeneous approximations here, there are some things which are related to continued fractions to theta. So some patterns of continued fractions here can come to inhomogeneous approximation. But because of the situation that we need to consider non-primitive approximation, you need to add some additional lattice technique. You need to have some filtration of lattices, and you just should use some properties of continued fraction approximations which survive during this consideration of filtration of some lattices.
Okay.
But in general, in one-dimensional case, it is very natural to consider something like Ostrovsky expansions. What do I mean? So you have continued fraction for theta, you have remainders for continued fraction for theta, and you can decompose the inhomogeneous part as a series with certain as a sum, in infinite sum of these remainders for approximation with certain coefficients. So theta n is Pn theta minus Qn theta minus Pn. So this is a rather standard argument, and sometimes it helps. So of course there are continued fractions, but you should use these continued fractions rather artificially.
Okay, well, I mean, the theorem says something about Pn and Qn, so I thought they should come from some continued fraction. Okay, anyway, I think I understand.
Fractions everywhere, yes, of course.
Okay, other questions?
So I have a question about your, I think, second last slide, where you were.
You are interested in last slide?
I think it's the second last slide,
Yes.
where you say that you are using translated lattices, shifted lattices. Probably the previous slide, I don't remember.
Chevalier.
Maybe maybe. Yeah, this one. So so you say you were using shifted lattices. So are you, so what is the exact Malher's or Minkowski's convex body theorem with respect to shifted lattice?
Well, at this slide, I am explaining the method. I'm explaining the method. Please have a look. So, if we have the method, in general, method works as follows. We have a certain, say, ordinary asymmetric body. So we extend it to have several integer vectors. So what do we use? We use we use the notion of successive minima. You see that when we deal with this homogeneous and inhomogeneous problem, we should use duality. So it means that to deal with inhomogeneous problem for theta, we should use homogeneous problem for dual matrix. So we should estimate the successive minima not for the parallelepiped itself, but for dual parallelepiped, and here we use Mahler's theory. But if we manage to construct a parallelepiped with maximal number of integer points, then it contains a fundamental domain of a lattice. And it is a very powerful parallelepiped, because if you shift it anywhere, it will catch an integer point. So it is not a Minkowski convex body theorem, but it is a very useful tool to construct somewhere a fundamental domain which we can take under our control. And then we can shift it anywhere. And we do not need any convexity to catch an integer point.
I see. Okay. Thank you. It was a very nice talk.
Well, thank you, thank you.
Thank
But
you.
today I'm speaking about rather simple results.
Other questions? Okay, if there are no questions, let's thank Nikolay for a great talk. Thank you.
Thank you.